take a look at the following situation. Let's suppose we have a function let's call this one f of x. The notation is not important. Let's say we have another function. Let's call this one g of x. And let's say we have a function that does this, which is h of x. And this is our x value, which is a. Step number 1. Can I say that near a, g of x is less than or equal to h of x is less than or equal to f of x? Would you agree with this? I'm not talking about here. I'm not talking about here. I'm talking about near a. Can I say that function h is sandwiched between g of x and f of x near a?
Yes.
Perfect. Number 2. If limit of f of x equals limit of g of x as x approaches a from either side and equals a number L, can anyone conclude for us from 1 and 2? From 1 and 2, what do you think the limit of h of x as x approaches a from either side will equal to, assuming both conditions are fulfilled? H is sandwiched between those two functions, f, g, and h, and both limits exist, and they are the same number. What do you think the limit of h of x as x approaches a from either side will be?
The same.
Absolutely the same. By the Squeeze Theorem. By the Squeeze Theorem. Some call it sandwich theorem. So when is this applicable? Here's an example. Let's say we are told that 4x minus 9 is less than or equal to f of x and is less than or equal to x squared minus 4x plus 7. For all x greater than or equal to 0. For all x greater than or equal to 0. We're asked to find the limit as x approaches 4 from either side of f of x. This is what we're asked to do. Bottom line, I don't even have the function. So this is an example in which I wouldn't be able to determine. If you ask me what is the limit, if my life depended on it, I would not be able to tell you because I don't have the function. But I have, number 1, the first hypothesis of the Squeeze theorem, which tells me that the function I'm interested in is squeezed between two functions. So I am literally given g of x right here, and I'm literally given f of x. Don't get entangled in the notation. It's not important. So I'm given a lower function, and I'm given an upper function. And I'm asked to find the limit as x approaches 4 from either side. So the first hypothesis is already fulfilled. What should I check? What should I determine now in order to find this limit?
Find the limit of 4 for both other functions.
Exactly. Find the limit from the bottom function, find the limit from the upper function. If they both exist and they are the same number, then I'll conclude that that is the same. Because both hypotheses, if they are if this is fulfilled, then both hypotheses of the squeeze theorem are fulfilled, and I can draw this conclusion. Excellent, well done. So then we find the limit as x approaches 4 from 4x minus 9, and we find the limit as x approaches 4 from this. Can anyone give us these numbers? These are polynomials. So there is no headache, no worries, no problems with polynomials. So what is this? Yes?
I can't see it.
So do you know how to pin the speaker? So you see this on your entire screen?
There we go.
So please have the entire screen so you don't have any problems. So what do you say?
Seven.
That's it. Do we all agree with 7? Everyone?
Yes.
Oh. Yes.
Let me know if you say no. It's okay if you say no, I'll show. What about this?
That is also 7.
Good. So then what do we conclude by here? By the squeeze theorem. I have to write this on the side so you understand where it's coming from. So what is this then?
7.
Also 7.
That's it. So this was an example of the squeeze theorem. So let's look at another. Any questions on this? Okay, can you upload, just show me one page or anything that you wrote, specifically this or something else. I just want to make sure that everyone understands what we're doing. The more you understand in class, the less work you need to do on your own. And that's my target. And then I would like to show another example. Like the limit as x approaches 0, x to the 4th cosine 2 over x. Should I wait for another minute?
Yes, please.
Okay.
Yes.
Please.
Just one page. No, there is no need to upload more than one. Okay. So we are looking at this limit. What do I have to do first?
Plug in 0.
Good, good. So where is this going when x approaches 0?
Zero.
Excellent. Where is this going when x approaches 0? from either side. Before you say anything, let me graph the function for you. With a 2 at the top or just 1, it doesn't matter. So from one side is infinity, from the other one is negative infinity. So now the question is, what does cosine of, even if you consider not D and E, what do you say about this? You can't. You can't say anything here, right? So this is D and E. Now you can say, well, 0 times D and E is 0. No. It could be, but we don't know. So this is a typical example in which we will use the squeeze theorem.
Do we use D and E because it would end up being 2 over 0?
No, it's because cosine will oscillate like this. It will not approach anything. So that's why cosine of an infinity, it does not exist. So this is a typical situation in which we have to use Squeeze theorem. But remember, Squeeze theorem has 2 hypotheses. I have to show the first hypothesis, I have to show the second hypothesis, and then I can conclude. So what would be the first hypothesis? I have to find 2 functions. This is this function. But I have to find a lower and an upper. See, here's how we do it. We start with cosine. We know that cosine is bounded. What does bounded mean? It has an upper and it has a lower. It cannot go to anywhere, like tangent. So what is the upper possible value for any cosine, and what is the lower possible value for any cosine?
0 and 1.
Careful. Let's look at the unit circle.
1 and -1.
Correct. -1 here. We measure it on the x-axis, and 1 here. So the smallest possible value is -1, and the largest possible value is 1. Okay, I'm getting close. I was able to put this in, but it's multiplied by x to the 4th. What should I do to all 3 sides to get this function squeezed in the middle? This is just part of the function I'm dealing with. What should I do to all 3 sides to get that function in the middle?
Would it be negative x to the 4th? And then
Multiply all 3 sides by x to the 4th, as long as it's not 0, which is not, and is definitely greater than 0. Because otherwise I have to switch the inequality symbols. Is x to the 4th greater than 0 for any x?
Yes.
Sure. Is it not 0? Yes, of course, because x approaches 0 means literally x not equal 0. Good, so let's multiply. What do I have left? What do I have in the middle? What do I have on the right?
Negative x to the 4th. Cosine 2 over x. Wait, no. How do you multiply? Would it be x 4th parenthesis cosine 2 over x?
Good.
Then x 4th.
That's it. So I found my f of x, and I found my g of x, which means that the first hypothesis is fulfilled. I found 2 functions that squeeze the function of interest. What is the second step of the squeeze theorem? What do I have to find in the second step or the second
The
hypothesis? Yes, so the limit as x approaches 0 from what?
The left.
From negative x to the fourth. And then I have to find the limit. I don't have enough room here. Then I have to find a limit as x approaches 0 from x to the fourth, which is this one. So the limit from this and the limit from this. What are they equal to?
Zero.
So what do I conclude?
That h of x is equal to 0.
No, I conclude that
Oh, the limit is 0.
of x to the fourth times cosine 2 over x is 0. And I have to write by the squeeze theorem. Both hypotheses are fulfilled by the squeeze theorem. Any questions? So this is a typical example, another typical example in which in the previous one, I didn't even have the function. I had no choice. How can I find a limit if I don't have the function? By squeeze theorem, I can do that. Here, I had a situation that cannot be handled in any other way. I cannot factor, I cannot rationalize, I cannot simplify, I cannot do anything. The only choice or option I have is the squeeze theorem. Okay, any questions? Always work on the WebAssign and everything else, and always come back to class with examples that we didn't get the chance to look at in class. If you have any difficulties, please always do that. Okay, I'd like to continue. Let's start 2.4. 2.4, as I always say, is the only proof in this class. Oops. In this class. Okay, it's the formal definition of the limit. In short, the epsilon delta definition. So you either call it the formal definition of the limit, or you call it the epsilon delta. There is a small delta and there is a big delta. Okay, uppercase, lowercase. These are Greek letters. So epsilon delta definition of the limit. So I would like to explain what it is, and then we will write it together. It looks and sounds fantastic. It's very simple. But it will look and sound very confusing at first. So I just wanted to warn you. Okay, so let's look at the graph of a function. So just bear with me. I'll repeat it and repeat it and repeat it as many times as you need. So here's a function f of x. Here is, of course, our famous a. And what is this? Our famous what?
L.
Of course, thank you very much. Sorry. Good. So, does the limit exist according to my graph?
Yes.
And the limit is?
L.
That's it. The limit exists. And here is the mechanism why it exists. If I choose a symmetric interval around L, so this point here is L plus a little bit. So epsilon goes with the y-axis, delta goes with the x-axis. Okay, so epsilon is on the y with the function value. Okay, here symmetric interval will be L minus epsilon. So if we choose an epsilon like 0.27, 0.01, small, of course positive. So if we choose, this is a number, whatever you want to say, let's say 10. So if I have 10 minus a little bit, 10 plus 0.1 and 10 minus 0.1, and I extend horizontally these lines from 10 minus a little bit and 10 plus a little bit and 10 minus a little bit, you see these horizontal lines meet the function somewhere. I come down with a vertical line from that point, come down with a vertical line from this point. So this happens for any epsilon, any number near plus minus 10 plus or minus that number. I can always draw these and determine a corresponding delta near A. So delta could be, see, this is a bigger delta. I'm going to call it delta, a smaller delta, delta 1. I'm going to call this one delta 2. From my graph, obviously delta 1 is greater than delta 2. So the limit exists automatically says that if I choose an epsilon near L, I will find the corresponding, for each epsilon, I will have to find a corresponding delta. If epsilon is 0.27, I will get a delta that is 0.1, potentially. If epsilon is 0.01, I will get a different delta. It depends on this, depending on where I start. So this dictates, right? So for every epsilon, I will find the corresponding delta near A, and I'll explain which one we have to choose, such that if I choose or pick X not further away from A than delta, so close, not here, not here, but close to A, that I choose an X, the function value of that X will definitely have to fall within epsilon away from 10. It will not fall below or above this interval. One more time. For every epsilon near L, I will find the corresponding delta near A, such that every time I pick X with a distance from A smaller than delta, not bigger than delta, then the function value will fall in the interval near L. I will put this in writing, and we normally use some symbols to put it in one row instead of half a page. Okay, so now, which of these deltas will I use? Will I pick? Will I pick the small delta, or will I pick the big delta? The answer is always the smaller. Always. Here's why. So if I choose the smaller delta, I'm safe. Every time I pick X here, I'll be okay, in the sense that it will fall within epsilon away from the limit. But if I choose the big delta, let's say I choose this interval. See what happens if I use the big delta? I may choose X here, and look what happens now. Outside of the interval. Okay, so what's all this? It's just a little exercise, basically. So I'm just going to write it with the following symbols. They're not a big deal. They're mathematical symbols, and there are 4 or 5 symbols that I recommend you put them in writing and you remember what they are, or just have them in writing. This symbol is an upside down A, uppercase A. It stands for every, or for any, or for all. This symbol, the backwards E, stands for it exists. There is, better, there is. I will find, if you want. This symbol stands for such as. It will just simplify everything in writing. That's all. You don't have to use them if you don't want to, but you have to write a lot. So how do we show, and what is the formal definition? So then the limit, we have to start with this at all times. The limit as x approaches a from f of x is L. The next is a symbol that is the equivalency, double equivalency symbol. What does this mean? This implies what I'm going to write next, and this implies this. It goes both ways. Okay. Since, of course, please continue here. Of course, I don't have, oh, let me continue here. Okay, for every, for any, for all, epsilon positive. And you can continue, but I have to move on underneath. There exists, I will find, a delta positive. One more time, let's stop for a moment. For every epsilon around L, I will find a delta around A, such that this distance from x and A is smaller than delta. So back to this. So the limit of f of x as x approaches A is L is equivalent to saying, or implies, for every epsilon positive, I will find a delta positive, such as, or such that, 0 less than the absolute value of x minus a less than delta. This only says that I pick x with a distance from a, x minus a, less than delta, means that x cannot be a. That's why we write greater than 0 and not, there is, why would I write that the absolute value is positive? No, I'm not writing that. I'm writing that it's not equal to 0, actually. So as long as we pick x close to a, this is the distance between x and a. The absolute value, x minus a, is the distance between x and a less than delta. This will imply that the function value, as I mentioned in the graph, the function value f of x minus L, the distance between the function value and the limit, what distance? This distance. The distance between the function value and the limit will always be less than epsilon. It's a mouthful. It's really nothing. And let me just show an example and we'll stop. So for every epsilon positive, I will find a delta positive such that when I pick x close to a, so that the distance is less than delta, it is guaranteed that the distance between the function value for this x and the actual limit will be less than epsilon. So let's apply this concept in one simple example, like limit of 1 plus 1/3 x equals 2. as x approaches 3 from either side. And I promise I know where is my, if I don't have my phone, I don't know the time. You will tell me the time because I can't find phone. Okay. So we are asked here to use epsilon delta to prove this. But first of all, is it true? Tell me if it's true. We don't want to waste our time. No, these problems will not be tricky. Is this true?
Yes.
Of course. 3 times 1/3 is 1, 1 plus 1 is 2. So now I can write the equivalency, the double equivalency. Ready for this?